In 2014, the qualifying exam for the US physics team had this as question 19. A helicopter is flying horizontally at constant speed. A perfectly flexible uniform cable is suspended beneath the helicopter. Air friction on the cable is not negligible. So which of the following diagrams best shows the shape of the cable as the helicopter flies through the air to the right? Is it A, hanging straight down, B, hanging diagonally to the left, C, this hook shape, D, the inverted hook shape, or E, kind of S bend? Now apparently there's been a certain amount of controversy about the correct answer to this question, so today we're going to go up in this helicopter and put this question to rest once and for all. Let's go.
Alright, we're all set. What up?
Here I'm deploying a battle rope, like you'd see at the gym. This one is about 15 meters long and it weighs 20 kilograms.
The whipping action beginning. I see it. So if we go really slow, will we avoid that? We'll see. Okay. We'll see when the rotor washstock's interacting with the rope and the ambient wind.
Now the setup looks pretty simple, but few people agree on what the right answer should be. When I polled YouTube, the most common answer was C. Well done on making that beautiful bell curve, by the way. We got in touch with the question's author, Professor Paul Stanley.
There were some creative students who actually constructed their own homemade scenarios. One had a fan to the side and another fan blowing downwards so that they could mimic the motion of the helicopter, and suspended a string and said, oh, it's this design. And the faculty members looked at it and said, oh, obviously, I can prove that the answer is this answer. They just didn't agree with each other.
If we approximate it as a chain of rooted links, I don't think we can just do that.
What do you think?
I think you're more likely to be C.
I think it is D.
D?
My guess is B.
What do you think? B?
I'm gonna go with A.
Interestingly, no one chose E. Have you locked in your prediction? To make sure the rope doesn't come up into the rotors of the helicopter, pilot Craig wanted to keep the rope on our right side so he could keep an eye on it.
Looks pretty good. I'm trying to make it look good. I mean, I'm really working on it. You're working hard.
So we're not going straight forward, we're actually going diagonally forward and to the left. But you can clearly see the rope is hanging straight, diagonally to the left.
That's a pretty good diagonal, man.
So the correct answer to the question is B.
Okay, you want to pull it in? Up it comes.
We're going to try a few more experiments, adding a weight to the end of the rope and then a parachute. But first, I want to discuss why the answer is B. There are two external forces acting on the rope: gravity pulling it down and air resistance to the left. When flying along at constant speed, these forces must be perfectly balanced by the tension in the rope. Now, when I set out to do this experiment, I wondered if the rope would be affected by the air pushed down by the helicopter's rotor. But judging by our results, this was not the case.
The rotor wash doesn't extend down below the helicopter all that far. It dissipates pretty quickly.
So you can consider the air resistance on the rope as entirely due to its motion through still air. Imagine dividing the rope up into many short sections. Each section has the same weight and experiences the same amount of air resistance because it has the same cross-sectional area and it's moving at the same speed. Now, the tension in any section of the rope must balance the sum of the air resistance and weight of all the sections beneath it. So the tension is zero at the bottom of the rope, and it increases linearly up to a maximum at the top. You can see the tension is small at the bottom of the rope. That's why it wiggles around while the top is much steadier. Now, although the magnitude of tension changes throughout the rope, its direction doesn't. And that's because the ratio of air resistance to weight is the same at every point along the rope. That is why a uniform flexible cable hangs in a straight diagonal line when pulled at constant speed by a helicopter. If the helicopter flies faster, the angle of the rope changes, but it still makes a diagonal straight line because the ratio of air resistance to weight is still constant along the entire length of the rope. But this got me wondering, what would happen if we added a weight to the end of the rope? Here I have a 20-pound, that's an 8 or 9 kilo kettlebell, and I want to ask you to make a prediction. What shape do you think the rope will make now? Will it still be that diagonal, or will it be one of the other 5 options? One more question for you. If we chucked a weight at the bottom, which shape would it be?
Probably the B or possibly C.
Does that change it?
Then I think it would be B.
Easy to do on the ground.
Alright, we're dropping the rope over the side. One has a 20-pound kettlebell off the end of it. How's that feel when it's dangling? No lateral displacement at all. Alright. How's your forearms doing? I'm feeling good. You know, I feel like this is the easy way, obviously. It's gonna feel different when I gotta pull it up. Okay, is it down? Yep.
Okay, let's give it a shot. Here the helicopter is flying at nearly 100 kilometers per hour. And the rope makes a different shape. You can clearly see it looks like an inverted J. This is option D. In fact, this is how the question on the qualifying exam originated.
So I taught for a semester in Hong Kong and would go hiking in the New Territories. One of the times I was hiking, I saw a helicopter fly with a cable beneath it. It was carrying something to one of the remote parts of the Hong Kong New Territories. And I saw the shape of the cable and thought to myself, that looks a little counterintuitive and very neat. This might make a good multiple choice question for the selection exam for the students. The cable that I saw had a weight hanging on the end, which gave it a certain curved shape. When I shared this with the other coaches, another coach, Andrew Lin, looked at it and said, I think the question might even be more fun if there is no weight on the cable, because that is even harder to imagine.
To understand why the rope makes this shape, we can use the same analysis as before, but now we need to add a large weight to the end of the rope. And this means at the bottom, the tension needs to be almost vertical to support the weight of the kettlebell, which has a lot of weight but not much air resistance. As you go up the rope, the ratio of total air resistance to weight for everything beneath increases. So the rope turns more horizontal in order for the tension to balance out that increasing air resistance.
More than halfway. You got it.
For the final test, I wanted to add something to the bottom of the rope that added almost no weight, but significant air resistance. So I picked a Veritasium flag, of course. So what do you think about hanging this at the end of the rope?
Well, you know, it's all science experiment for me, because these are all the things you never do with a helicopter and a rope.
What would be the real risk? Like tail rotor or this rotor, or both?
Either, any kind of this inner tail rotor would be destruction of the aircraft.
Here we go.
Now the rope still seems to be pretty straight. I think it's because the flag isn't actually adding much drag.
Still looks pretty straight, interestingly.
So we decided to add a small parachute to the end of the rope. All right, let's try it. But the concern here was that the parachute could get flipped up into the rotors during deployment, so we bundled the chute up into a backpack.
Very nice. halfway done.
Did it deploy more than that?
No, but once we start moving, it's going to grab a lot of air.
Now, with the parachute at the end of the rope, it makes a J shape, which is answer C. With extra air resistance at the end of the rope, but not much weight, the tension has to be virtually horizontal. And then as you go up the rope, the ratio of total air resistance to weight for everything beneath decreases, so the rope becomes more vertical to balance out the increasing weight. So depending on what's on the end of the rope, you could get answers B, C, or D.